Well, I think I just turned everything on, so we can probably start with the first lesson in this course on artificial intelligence. Uh, well, it is 7 a.m. in the morning and I haven't slept all night actually, because I was preparing this script right here. Well, it's not a script, it is probably like an outline. But anyways, this course is meant to be, well, not an introductory course per se, but an all-encompassing one on the field of artificial intelligence, but we won't cover everything in too much depth, because to be honest, I'm not an expert in this field, and English is not my first language, as you can probably tell. But I would like to use this course as a motivation for myself, because I actually learned from experience that I learn new topics the best when I teach others. This is also known as the Feynman technique. So it is here to motivate me to study and to cover the things I want to cover. And by teaching you guys, hopefully I can get other people interested, and you can use this as a study guide or reference. I will actually be covering the courses from the book Introduction to Artificial Intelligence, and I have a digital copy of the script right here. I will be covering the fourth and the newest edition, and it is a book written by Stuart J. Russell and Peter Norvig. It is used at many universities as a formal literature for the courses on artificial intelligence, so I thought it would be a good way to start learning the field. And we'll be covering the introductory courses in this episode. You will probably notice a lot of cuts in the video because I make a lot of mistakes, and please be sure to correct me in the comments if you find any mistakes, because like I said, if you're looking for an expert in the field, that I'm not. So I think we can start by looking at my outline right here. I guess we start at the basics and cover what the field of artificial intelligence. I have a blackboard prepared here. I was also thinking about recording in front of a real whiteboard, but I had a lot of problems with the lighting. So I think this would be the better option, to just record digitally, because I also have a graphic tablet on which I can write. I don't have the one with a display, but I still think this one will use. So what is actually AI? What does it cover? Well, let me just write here, AI introduction. So, the field of artificial intelligence is a subfield of computer science, a pretty new field in that regard. The research and the field of study actually originated around 70 years ago, but the basic sciences from which it gains inspiration go a lot deeper in the past than that. The main goal of artificial intelligence, the creation of intelligent entities or agents. Agents, from the Latin word agere, which means to do. So an agent, in the most basic words said, is just an entity that does something. But how do we define an intelligent agent? What is an intelligent agent? Well, we first need to look at how we define intelligence itself. And we'll take a look at that a little bit later on. But first, we need to talk about the fields from which the AI originates from. And some of the most obvious ones would be the discrete math, the computer science, electrical engineering, because the electrical devices are the mediums in which we implement these intelligent agents nowadays. That might change in the future with the advance of quantum computers. It also relies heavily on the probability theory, on statistics, and calculus, linear algebra, and so on. And it has an impact from the little microelectronic devices to the interplanetary explorers, such as the rovers, on which the AI systems are implemented on. It has an omnipresent social aspect as well, because it is one of the fastest growing fields nowadays. I think it's a universal field of study that is worth your time and worth the efforts to learn. I previously talked about defining the intelligence and human intelligence in general. Well, we as a species are called Homo sapiens, man the wise, right? So how do we define intelligence itself? Are we the only intelligent creatures? Are other animals also intelligent? And when building these entities that are intelligent themselves, do we build the entities that just act like we do, think as we do, or not think and act as we do in general, but behave on some aspect of objective rationality and think rationally? So there are 4 different approaches in the field of AI, and we will talk about every one in particular, and what are the benefits and what are the most accepted ones nowadays. So the first one I would like to cover is modeling the human behavior. And one of the most important aspects of this approach is the one and only Turing test for intelligent entities and agents. It tries to define if the agent is intelligent, and it relies on the interviewer asking the interviewee or the intelligent agent questions for an extended period of time, and then figuring out if the entity responded like human would, and if the interviewer can tell the difference between the answers, if they are given by a machine or a human, then the entity or an agent could be classified as an intelligent system. It also relies on the many fields of artificial intelligence to pass the test. For example, the knowledge representation searching algorithms that would be needed, also natural language processing, which is one pretty important nowadays. But it also extends to a complete Turing test, which checks if the interviewer can't tell by looking at the entity that is replying to him if it is a human or a machine. So that will include the fields of computer vision and also robotics, because it needs to manipulate objects and prove that it's human and not a machine. Turing, relying on this one approach of human behavior, designed a pretty important model for testing intelligent system that is still relevant nowadays. Human thought approach, by modeling the intelligent system such that they think as humans, yielded also some important advancements, such as the rise of neural networks that are similarly modeled to the human brain and the way neurons work. It has since been proven that the best approach would be modeling the agents that can think, and even better, just act rationally. Because humans are not per se irrational creatures, but there is also some margin for human error always included. So creating an agent that can just think like a human wouldn't be the most beneficial. It would actually be more beneficial to create a one that performs even better than humans in most situations. Also correct me please if I make any spelling mistakes. But the more beneficial ones have proven time and time again to be the rational thought approach, so this model actually tries to create the rational agents, but that are based on the objectional rationality rather than human-like thought, and it has been proven as a superior way of creating agents, but not the best way per se. It relies on the definition of objective rationality as a choosing the best out of the possible things to do at that very moment. The most appropriate thing to do in a certain setting is many times not that obvious. We can try to find the suboptimal solutions in many cases. This approach started in ancient Greece with Aristotle and his syllogisms. I hope I pronounced that right in English. And it is trying to define a formal way of getting to conclusions and making inferences from formal notions. In the modern times, we have concluded that the formal way of representing is not always the most optimal, and sometimes the starting definitions or theorems or axioms in a system just cannot be represented that way, because it is, for example, based on probabilities, and You need to use some statistics to arrive at the solution, and it is not pre-known. So our best bet would be to create a rational agent that just acts rationally, and it is the most optimal approach also because it is the most scientific one, as we can always test our hypotheses and check how the agent is acting in that regard in certain settings. And we need to represent the thought as a way of choosing our optimal answer, but it is much more important how the agent acts, because that is what we perceive and not just the thought modeling process. And also, the most optimal solution sometimes does not arise from the just rational thought. You sometimes need an agent to act a lot quicker than it would when making inferences, and one of the most basic examples of that is touching a hot stove or any hot item. In that case, if you just try to rely on your thoughts and inferences, you would probably get burned. But if the agent reacts on a kind of reflex, it is a much better solution. So we cannot just model the thoughts, we need to take into consideration all the possible ways our entity needs to act. Creating that intelligent entity is considered in this way a standard model of creating intelligent agents in artificial intelligence, because it is the most widespread. It relies heavily on theories from economics and control systems, and also optimizations and process theory, process optimization. But it has some a priori problems, and they arise in some more complex systems where you cannot define the rational way to do something just by creating an agent with a simple goal, because the goals are not always so simple. For example, in autonomous vehicles, you cannot just tell an agent to drive in the fastest way from one location to the other, because it may run some people over on the way, or it can try to manipulate the scenarios and its environment just to fulfill that goal the quickest way possible. So we need to be very cautious with that approach. And it also has some problems in environments with limited rationality, where there is not always, you cannot just always consider every possible solution and select the best answer. So the suboptimal solution would be actually the best one in that case, if you are quicker to arrive to it. Creating an agent that is not completely aware of the objective goal, and it serves in a kind of a utilitarian way to the people, would be the best approach all around. That is called an alignment problem, and it is a very important topic in modern artificial intelligence. So why is it so important? Because the intelligent agent could, as I already said, could try to manipulate its environment in a way that would benefit the ultimate goal, but it may not actually benefit the humans the most in that way. And there's a funny saying that they also cover in the book. It's by an old chess player, Ruy Lopez, which he played in, I think, the 16th century. And he said the best way to gain an early advantage on your opponent is to place the board in a way that the sun would get in his eyes. So it's a funny way to think about how the AI tried to manipulate just to achieve the common goal it was set to. So now that I covered the basics, I would like to take a look at all the sciences that the artificial intelligence, the field of artificial intelligence, and this subfield of computer science in the modern world takes the inspiration from. And you will see that the list is pretty long. As I already said in the beginning, it is probably one of the most universal fields of science, and it takes inspiration from a lot of different sciences, some social ones and some physical sciences, and even some formal sciences like math itself. And I would start with the philosophy, and we already kind of touched on philosophy, and I would read to you some of the questions. How the mind actually arises from a physical structure of the brain. Is consciousness just an illusion, and free will is just an illusion that arises from the mental processes that happen in our brains, or is it a valid thing? Another important question for AI is where the knowledge comes from and how do we store it, and how it leads to action. How does the knowledge we have in a system lead to its action? How do we arrive to actions from the represented knowledge we have? And can formal theories be used to create conclusions? And many great minds from the past touched on some of these topics. For example, Blaise Pascal, Leibniz, the Newton's rival, as many know him as. And they tried to, and sometimes even managed to, create devices that could represent some kind of automated reasoning or calculations, to be honest. They were nothing too advanced, but nonetheless they created the base for the modern systems we have today. And Thomas Hobbes was the first one to, I think, at least, well, probably the first one that we remember of. He was of the opinion that we can create an artificial mind because the mind itself is nothing but a physical entity, and so we could try to replicate it with, for example, mechanical systems, the workings of the mind, however complicated they may be. On the other side, there's René Descartes. Suppose the mind is not just a physical entity that can think, but there is some kind of dualism and spiritualism hidden behind it. So is free will an illusion of our internal thought process? Or is it part of our soul that is somehow not connected even to our physical body? Another important topic for AI that relies on philosophy is where the knowledge comes from, and I think the empiristic movement gained the most traction in this field, and it says that nothing is in the brain or memory that was not first in the senses. So we actually gain our knowledge through our senses. When thinking, we actually just rely on the knowledge gained from our senses. All of these philosophical theories also advanced in the modern age, or well, not some modern age, with the great minds like Bertrand Russell, Ludwig Wittgenstein, and the Vienna Circle working on them. But I would like to touch on the Aristotle once again, and he had a quote saying that the action is nothing but a connection of our knowledge and our final goal. So the action just represents, so to speak, a way to connect our thoughts and the current situation to the goal, just optimizing the way we arrive to it. And that is pretty much the same notion we covered earlier, where the intelligent systems just try to optimize the way to their solutions. As a final topic in philosophy, utilitarianism and Immanuel Kant's deontological ethics. Kant's deontological ethics rely on making the most morally objective approach and action in every case, but contrary to it is utilitarianism, or a kind of consequentialism, I think it is how you pronounce it, which says that we do not in every instance have to do the most morally objective thing, but we can do the morally wrong thing if it is in the better of mankind in general. It is a pretty simple way to put this stuff, but I won't cover this stuff in much more detail because, first of all, I'm not a professional, and second of all, I think we can just gain a bird's eye perspective on this concept, and that would be enough for what we are touching on here and what is the main purpose of this course. So the next field I would like to cover is mathematics, and I just noticed I haven't written anything at all on the board because I now try just to explain the concepts in general, and I don't need a lot of writing or mathematics implemented on our blackboard, not a whiteboard. In math, we have some overlap with the philosophy in the terms of questions of can the formal rules be used to arrive at the correct conclusions, but we actually try in math to model these formal rules and not just ask if they can be formulated. And the field that covers that pretty much in depth is mathematical logic. And it started with the formal theories in general and the development of Boolean algebra by the great George Boole. But yeah, pretty much relied also on the computational theory, which arose from the Alan Turing and his mentor Church, and it is covered by the Turing-Church thesis. It also pretty much relies on the probability and statistics and many great minds also worked on that. And one theory which is also very important is the, as I already said, theory of computation, computational complexity, and algorithmics. Some of the formal knowledge representation we will actually cover in a later part of this series in a course regarded to the first order logic. The algorithm is a pretty much hard thing to describe with mathematical formality. You can try to gauge the definition as a kind of a set of rules or a set of steps formal set of steps you can follow to just arrive at the solution. But it's not a very formal way to do it. So the Alan Turing, one of the founding fathers of computer science and the field of AI, proposed a modeling machine model that will quite well represent the algorithm in a mathematical and formal way, and it is called the Turing machine. We don't have a lot of time to cover it in depth, but I would recommend you to go and take a look at how the Turing machine works and how it defines the way we do computation. The problem of tractability arose very early on. It is much more easily done optimizing your algorithm in a way that it performs faster and with a lot less memory usage than to actually just create new machines, so on and so on. And it is in many times the only practical solution to a problem. And in that way we arrive at the famous Millennium Prize problem called P versus NP, which is the set of polynomially deterministic problems and the set of polynomially non-deterministic problems. And the polynomially deterministic problems can actually be solved in polynomial time. These problems can be solved in a reasonable amount of time. Contrary to them, the polynomial non-deterministic problem can't be deterministically solved, which means arriving at the most optimal solution and the most optimal solution out of all of them. They cannot be represented in a polynomial time, in a function of polynomial time, but rather just the exponential one in a deterministic way. Sometimes arrive at the suboptimal solutions in polynomial time, but we cannot arrive at the most optimal one. And the set of NPC problems or NP complete problems is the set of most complex problems, which if they can be solved in a polynomial time would prove that any problem can be tracked down to a polynomially deterministic one. So that would be everything I want to cover in math. Next one is economics, and economics is not just about money, as many people are used to thinking. It is actually a science that covers how we arrive at the decisions based on our preferences and the actual payouts in the future. It also tries to cover what happens when we do not have the support of others and how the impact of others impacts us. The economics has its beginnings as a formal science, at least, in the book Wealth of Nations, which was written by Adam Smith, covered how the set of intelligent entities or beings were working with a common goal of their own well-being. Another field of economics that is of importance to AI is game theory, first formalized by John von Neumann, and if you have time I would also recommend checking with his Wikipedia article. He was a polymath from the 20th century who had an extremely wide-ranging impact on many scientific fields. And the game theory based on getting to the most optimal solutions or decisions based on the ultimate product of many individuals impacting each other. Contrary to that, the theory of decision making is just based on the decision process of getting to the most optimal decision when not taking into account other entities that would impact each other in that regard. The theory of operational research also has an impact on artificial intelligence because it actually covers the sequential decisions and their ultimate results, which economics in that way did not try to explain as far as I know of in the beginning. So it has an impact on the development of multi-agent intelligent systems that are created from many individual ones. And we also borrow some of the techniques like Markov decision processes and chains. Neuroscience, on the other hand, tries to explain the thought process itself. And we can try to cover this topic by approaching it from a logical side and the advancement of our understanding of the human brain and its workings. And it probably would be the best way to start at Santiago Ramon y Cajal. He was a Spanish scientist and he was a Nobel Prize winning one. And I took a picture with his Nobel Prize in Madrid, in the Natural History Museum of Madrid. He was the first one to model the anatomy of a single neural cell called a neuron, as we know of today. And the neuroscience also borrowed some of the techniques, such as neural networks, as I covered earlier. They are actually one of the ways we can create our modern intelligent systems nowadays, and they take inspiration largely from the neuroscience and the anatomy of a human brain and how it is modeled by the electrical system. And the advancements of MRI, electroencephalogram, and the other modern techniques in which we can actually view the workings of the brain internally have yielded a lot of important results. Another important crossroad of these two sciences is the brain-machine interfaces, and the most modern one I can think of is the Elon Musk's Neuralink, which tries to define our brain workings in a certain kind of sense and improve our memory, and the brain-machine interfaces in general try to improve the workings of the brain, particularly brains of the people that were in some kind of accident or have some kind of disability, and try to improve their quality of life. Also, ultimately, we try to arrive at the time where the intelligent systems we created can not only work in a way that our brain can, but exceed the limits of our own brain. And the point in time in which that happens we call singularity, and it is also one of the buzzwords very frequently used in the artificial intelligence world. Psychology, on the other hand, tries to answer how humans and animals think, and it also has yielded, at least the scientific side of psychology, some of the more important insights which we use in the field of artificial intelligence. For example, the Helmholtz's research of the physical side of human vision and the creation of cognitive experimental psychology laboratories. We differ two approaches here in understanding of the workings. The first one is the biological behavioristic approach, which tries to model the workings of the brain in a way that only relies on watching. And as you can probably tell, I just magically changed my clothes. Well, sadly, the last time I was recording, my camera turned off. It got too hot real quick and I have to cover some things over again. And it's a brand new day and we can continue. I was thinking of covering all of this in one sitting, but sadly that wasn't possible. And I can continue where we left off, but first of all, just some words on how I was thinking of approaching this course. From the last recording session, I got to the conclusion that it would probably be better to create some kind of animations in the background and not just with me writing while I'm talking. So I will probably implement that if I get the time for it. And the videos will be a little bit longer. This first one will be 30 minutes long, approximately, and the later ones will be closer to an hour long. And I just hope that I won't make the same mistakes as I did in this video, because I had a lot of trouble editing it. And let's just hope that I get better at this with time and it doesn't take so much time for me to create as I get better at presenting and teaching, especially in a foreign language. So we left off at the biological behavioristic approach in psychology that is a lot more beneficial for the creation of AI systems than the traditional approach, which takes into account also the internal thinkings and it relies on introspection more so. Behavioristic approach is similar to the one in biology, where we just try to gauge the actions of individuals or creatures in biology, and by that we get to the conclusions and create a model for how they function. Cognitive psychology tries to see a brain as an information processing device, which is pretty similar to a computer program that takes an input and creates an output. We also need to touch on differences between artificially intelligent systems and the augmentational intelligent systems that try to augment the already existing intelligence of humans in comparison with the artificial intelligence systems that are almost by definition completely autonomous. In modern times, these concepts are pretty similar, and they sublimate, I hope that's a word, it is in my language, to more or less the same thing, because truly autonomous systems today do not really exist. They still just augment the existing intelligence in humans. As I previously mentioned, the medium in which we implement these systems in modern times are electrical devices, and in particular the modern computers. Computer engineering as a branch of science is one that is between the computer science and electrical engineering, and is one of the offered courses at many universities in foreign countries and also in my country. My module is actually called software engineering, just as a side note, but it is as a program more similar to the foreign computer science and engineering, but this one is more geared toward the hardware side of things, and it has its origins in also Turing's team that tried to break the Enigma code during the World War II. Their computer wasn't actually an electrical one completely, it's part electrical, part mechanical device, but soon enough these new electrical computers, complete electrical computers, were emerging, and they had their beginnings in the vacuum tubes, but with the invention of transistor, which created a really giant leap and also provided some of the Nobel Prizes in physics, these electrical devices were improving exponentially. And Konrad Zuse created the first programmable computer called Z3 or Z3, but ENIAC is today considered to be the general ancestor of modern computer devices. We can also mention Moore's law. Moore was one of the founders of Intel along with the physicist Robert Noyce, and he formulated that the number of transistors would double every 2 years. And more or less so, the technological advancements followed this curve for a pretty long time, sometimes even suppressing it, and sometimes falling a little bit behind, but more or less so it was following the Moore's law. And the modern systems are believed to take on the concept of parallelism and to improve on that aspect the efficiency of the new systems and technologies. And we can see that in the advancement of the GPUs in some of the previous years, and also the development of TPUs or tensor processing units that provide the AI models a best medium to train it on. It also reflects on the great increase of the Nvidia's stock price. And the model that took almost a day to train, 2014, can almost be trained in less than 2 minutes today. This parallelism is actually in congruence with the workings of the human brain, which is another interesting overlap in the theories of creating intelligent systems and the existence of already existing ones. Quantum computers also can be used to more quickly solve a particular set of problems in artificial intelligence systems and agents today. Control theory is second to last branch I would like to cover before we finish this, and its field of study focuses on the artifacts that can work autonomously. And One of the first inventions was a water clock with a regulator of flow. It was a creation in the ancient times, and it redefined what we consider an artifact be able to do. The mathematical model which it uses was first formulated by James Clerk Maxwell. He's also the scientist behind the Maxwell equations in physics and electromagnetic theory. Another important name is Norbert Wiener. He was also an influential mathematician, and he formulated this control theory in general as a way to minimize the differences between the goal and the current situation. And that is a notion that we kind of already heard of in the Aristotle's way of representing the goals and ambitions and the differences between them. Control theory is mainly focused on homeostatic devices that are controlled by the feedback loops that constantly control in an autonomous way its output. And one of the fields that is pretty important to AI is stochastic control, which deals with uncertain and statistic artifacts and functions. These are pretty similar topics, but AI has a lot broader field, and that's why they are not the same field of study. AI also tried to cover languages, vision, planning, perception, and also learning from the previous behaviors, the concept today known as machine learning. The last one I would like to touch on is linguistics, and there was a battle between two different approaches in what we believe language is and how do we speak and represent our knowledge. And the behavioristic Skinner's approach thought that all of the sentences are just a congregation of what we already know, but it failed to take into account the creativity, for example in toddlers, that could create new sentences and form new sentences that they did not hear before, by using the knowledge to represent something completely new. The linguistics is very close in its nature to the natural language processing. They constitute the field known as computational linguistics. The problem of knowledge representation and processing the natural language proved to be a lot more advanced than we originally thought, since you need to take account even the context and not just the structure of the language when creating sentences from nothing. I think I covered everything I wanted in this first lesson. Maybe it was a little longer than I thought. As I said, I would try to create more interactive animations for the further episodes and to be more natural and relaxed, I hope. So this was the first lesson covering the introduction and some of the basic terms, and in the next episode I will briefly cover the history, and then we can jump to actually creating intelligent agents and different fields of artificial intelligence itself. And those videos they are a lot more technical than this first one I created. So I hope I didn't bore you to death, that you were able to persevere through this video, and I'll hopefully see you in the next one.